Hello everyone, I am Kyoung-Hee Kim, a professor of architecture and director of the Integrated Design Research Lab at UNC Charlotte. Welcome to this presentation on renewable energy building integration with a focus on BIPV's engineering principles. These two books, Building-Integrated Photovoltaics, a handbook, and A History of Solar Power Art and Design, provide foundational knowledge on integrating solar technology into building design. The table on the right summarizes key engineering requirements. BIPV is an integral part of the net zero architecture and consists of several components. Because BIPV modules serve multiple functions as power generators and building enclosures, their design must ensure typical building enclosure performance requirements, including structural integrity, electrical safety, life safety, waterproofing, energy performance, power production efficiency, longevity, recyclability, and quick ROI. Understanding these components and their integration provides a foundation for discussing the engineering principles that influence BIPV performance. Please refer to an additional video focusing on BIPV's design principles. This slide illustrates the key components of a BIPV panel. It includes a glass cover, solar cells, and a back panel, which are clamped with metal perimeter frames. The electrical connections between the solar cells lead to the junction box. BIPV panels are securely anchored to primary structures, preventing detachment or structural failures during wind, seismic, or climate disaster events. Building on the structural assembly, the solar panels are assembled into a BIPV curtain wall system. As shown in the figure on the left, the solar panels are integrated into a spandrel panel of the curtain wall. Curtain wall consists of spandrel panels which conceal the floor slabs and vision panels which allow view out and daylight penetration. The spandrel panel is an ideal location to integrate high-efficiency solar panels. Because BIPV curtain walls serve as primary building skin, they must be constructed to provide a waterproofing assembly, protecting interior spaces against water intrusion. Water leakage not only poses structural problems, but also causes mold growth, which can threaten occupant health. Now let's look at system safety. Electrical safety during the BIPV system assembly and installation is critical. BIPV systems incorporate safe electric wiring, insulation, and grounding to prevent arcing, electrocution, and electrical fires. The BIPV system needs UL certification and must meet safety standards according to IEC, ASTM, and NFPA. Once the system is fully certified, real-world installation must comply with life safety and fire resistance requirements to protect occupants and firefighters. The installation must integrate rapid shutdown measures in case of any shock or potential fire. The figure at the bottom illustrates the connection between solar panels, rapid shutdown, battery, inverter, and net meter device. When solar power is not available, the utility grid supplies the power directly to the building. When the BIPV system is coupled with a battery and can supply power to the building, the solar-generated DC is converted to AC through the inverter to power the building. Any excess power in this case is sent back to the grid through a process called net metering. This slide shows BIPV's energy attributes. The figure on the left shows a BIPV curtain wall, which consists of solar spandrel panels and a vision panel. The vision panel uses a high-performance insulated glass unit to regulate unwanted solar gains, maximize daylight transmission, and maintain a good U factor. The solar spandrel panel is opaque and is responsible for thermal insulation. There is batt insulation behind the solar panel, where the solar panel generates power while shielding against weather. Such an energy-efficient BIPV curtain wall helps reduce energy consumption or even achieve a net energy negative building and enhance occupant comfort. Turning to electrical output, the product of electric current and voltage is solar power. Greater current and voltage mean higher solar power output. The line graph on the left shows IV curves under different solar intensities. The maximum power occurs somewhere along the IV curves, between the short circuit and the open circuit. For example, under 1000 watt per square meter solar intensity, the solar cell produces about 8.5 amps and 0.5 voltages, resulting in 4.25 watts for that solar cell. When additional solar cells are connected with a series electricity connection, the total power increases because the voltage from each cell adds up. In addition to solar irradiance levels and connection types, solar power production is impacted by temperature, partial shading, and dust. To optimize electrical output, bypass diodes and smart monitoring can help avoid hotspots. A BIPV panel produces its maximum power when it receives the sun directly. Therefore, different geographic locations receive different amounts of irradiance due to the Earth being a globe and tilted. A solar facade located in Freiburg, Germany, would have the maximum power production when the BIPV facade is located in south-facing tilted plane, highlighted in brown in the building at the bottom right. Therefore, it is important to understand the optimal tilting angles of a BIPV system for different facade orientations to receive the most incident solar rays. This illustrates that as the angle between the panel and the sun's rays increases, the effective solar irradiance on the panel drops approximately with the cosine of that angle. In other words, if sunlight strikes the panel at an angle, the projected area receiving radiation is reduced following the cosine theta law. For example, when a solar panel is too flat, it may lose morning and afternoon sun. When one is too steep, it may underutilize high midday sun. In the context of solar facades, which are usually vertical, this means they are optimally angled for low winter sun, but receive less direct radiation in summer when the sun is high. Therefore, optimal tilt angles depending on the facade orientation help increase power production. Slide 11, 12, and 13 illustrate how partial shadow caused hotspot and power production loss. Partial shading negatively affects BIPV performance. Shadows are created by adjacent structures, trees, and even the building's own architectural features. Solar cells are usually interconnected in a series configuration. When shading affects even a small fraction of the panel, it limits the flow in the entire electric string, restricting the overall system's current. Continuing the discussion on the effect of shadowing, this slide shows how rooftop solar panels receive different shading conditions based on their installation location. If solar panels are located in zones 1 through 4, these rooftop HVAC units and similar obstructions will cast partial shadows on the solar panel. As mentioned before, partial shadows affect electricity production and system longevity. This slide shows a thermal camera image detecting hotspots on a solar panel surface caused by the electric current bottleneck due to partial shading. These localized temperature spikes reduce efficiency and degrades the panel over time as heat buildup stresses the solar cells. This is why BIPV designs should include a shadow analysis to prevent potential shading issues during any time of the day and any period of the year. While implementing bypass diodes in modules or mini bypass diodes between cell strings may mitigate some of the shading losses, reliable power production and system longevity can only be ensured when shading is fully or mostly avoided. Shifting from operational efficiency to life cycle considerations, this slide explains the importance of the recyclability of solar panels. It is important to take a holistic approach that considers all stages, from initial planning and operation through to the end of the life cycle. As the widespread use of solar panels increases across the globe, planning and implementation for retired panels, including collecting, dismantling, material recovery, reclaiming, and recycling, become essential. Circular economy strategies help ensure that BIPV systems remain a clean and sustainable energy source. Compliance with future recycling regulations, along with financial incentives, will support circular economy practice. Current recycling techniques allow up to 95% of solar panels materials to be recycled. Global PV waste was 250 kiloton in 2021 and is expected to increase to 78 megaton by 2050, with an annual growth rate of 30%. Beyond environmental and technical performance, we must consider the return on investment. A shorter ROI is another way to implement widespread adoption. It means how many years it takes for energy savings and financial incentives to equal the system's total upfront costs. One primary contributor to shortening the ROI is through greater energy cost savings, with a higher conversion efficiency that can offset the upfront cost. Some claim their solar panels have an ROI of 4 years. For example, if a solar panel system costs $10,000 and saves $2,500 per year in electricity costs, the ROI or payback period is 4 years. While BIPV offers multiple benefits, widespread adoption still faces several challenges across economic, technical, regulatory, industry, and educational domains. On the economic side, high material and system costs, coupled with limited financing and bank support, make upfront investments difficult. Technically, because BIPV systems are integrated into buildings, they experience lower efficiency compared to optimal standalone solar farms. In addition, they can have design conflicts when blending solar performance with architectural requirements. In terms of policy and codes, regulations have not kept pace with innovation. In other words, there are often no clear standards specifically for BIPV applications. The industry also faces growing pains. The supply chain for BIPV components is relatively immature, and integration into conventional construction practices remains limited. Finally, there are educational and awareness challenges. Few public demonstration projects have been built, leading to low public trust in technology. In addition, there is a lack of trained professionals and curriculum focus on BIPV in the architecture and engineering fields. In the following slides, we will examine each of these challenge areas in more detail. Let's look at economic challenges. The cost factor remains one of the biggest hurdles for BIPV adoption. Specialized PV integrated building components tend to have high upfront costs compared to conventional construction materials. There is limited governmental financial support. Private and bank financing is also insufficient, making it difficult for many projects to move forward. Beyond economics, BIPV efficiency is relatively lower than that of solar farms or rooftop PV. This is largely due to non-optimal orientation, partial shading from adjacent structures, and limitations in ventilation that cause overheating. Systems still have room to improve technology that accounts for BIPV applications. Ongoing developments are semi-transparent, bifacial, and colored PV modules that better balance performance, aesthetics, and user experience. A lack of integrated modeling software is another hurdle in high-efficiency system design. It is important to run a holistic consideration of planning, analysis, implementation, and management of operations and maintenance, but there is still a gap in tools that support the full life cycle of BIPV systems. In addition, clear and unified standards for BIPV are not available. This creates uncertainty in code compliance and project approvals, often causing delays or added costs for project implementation. Another significant barrier for wide implementation is the limited awareness and expertise related to the BIPV sector. At present, there is a lack of trained professionals and curriculum alignment with BIPV in the architecture and engineering fields. Few university programs or professional training courses emphasize integrated solar design, and comprehensive project life cycle, resulting in a shortage of practitioners confident in advocating and deploying BIPV. On the public side, few showcase projects have been built to demonstrate BIPV in real buildings. Addressing these issues of education and public awareness requires BIPV coursework and continuing education, along with more public demonstration installations to increase public trust. This video was supported by UNC Charlotte in collaboration with the US ASEAN Smart Cities Partnership. For further inquiries, please contact Kyoung-Hee Kim at UNC Charlotte. We look forward to advancing BIPV technology together.